I could probably give you a 2 or 3 hour lecture and still not fully cover everything there is to cover here. So my intent here is not going to be to exhaustively cover the science here, and I'm quite certain I will not be able to do it justice in the time frame allowed. But on the other hand, I know that unlike me, I think there other people have things to do today other than just talk about static people. So I will try to keep my remarks within the allotted time period. So a little bit about me. Mark already gave the introduction. So I actually didn't start off in nuclear engineering. I started off in physics, and I worked on high energy physics. I worked on some of the really cool cutting edge nuclear physics, like the quark-gluon plasma. So how many here have heard of the Higgs boson? Okay, so I wasn't working on Higgs boson. I wasn't working on anything that cool. I was working on similar slides though, heavy ion collisions to look at confirming the very basic structure of matter at the beginning of the universe using similar instruments like the LHC. So I was at the Relativistic Heavy Ion Collider, the RIC, in Upton, New York, where they keep thinking we're going to make black holes. We haven't yet. And really, after I got my master's degree, I had a bit of a career change. The short version of the story is that I was at a Thanksgiving dinner, and I was near the end of my master's degree, and I was helped up talk about my heavy ion physics research with some of my extended family, and one of my cousins listened and politely nodded, and I was explaining all the intricacies of the Big Bang and quark-gluon plasma, and he finally just said, "So that's interesting, so how does it help people?" And I gave a very hand-wavy answer about how we don't know where science is really going to take us, but we have all these things in the digital age that came about because of quantum mechanics at the turn of the 20th century, so who knows what this will do? But at the end of the day, I knew that wasn't a very satisfying answer. And that kind of led me on a pathway to where I really began to think about what I wanted to do with my career. And at the same time, it was becoming increasingly clear that the threat of climate change is both real and significant. And so I realized I wanted to take my love of physics and problem solving and put it to use to somewhere where I felt like it could make a difference in helping to preserve the quality of life we've come to enjoy, while also doing my part to help combat a significant and potentially catastrophic global threat. And so I actually went back to my Ph.D. at NC State University, and I worked for an advisor, Dr. Mansong Yin, who was very similarly motivated at solving kind of some of the big social challenges. And he was very focused on the social challenges inherent in nuclear engineering, and that really rubbed off on me, as you'll see here. So after that, I spent some time at the reactor physics group down the street at Oak Ridge National Laboratory, and in 2012, I've come here, serving as an assistant professor in the Department of Nuclear Engineering. So, to get me started here, a lot of times, the biggest question or the biggest issue we think of when we think of nuclear energy and the nuclear fuel cycle is inevitably the problem of waste. What do we do about nuclear waste? And I think this is a central issue that I think we need to be able to illustrate as engineers to the rest of the community that this is a solvable problem. So before we can really achieve a wider spread acceptance of nuclear energy and expanded use as a climate change mitigation strategy. And I think this is a solvable problem. I think it's solvable through the application of things like smarter techniques for the nuclear fuel cycle, including recycling the components of nuclear fuel we can reuse in advanced reactors. But to do that, we also require bringing to bear some more advanced reactor physics tools. So extending our knowledge and understanding of physics to new domains, to more advanced types of reactors that can act as consumers of these long-term radioactive wastes. And meanwhile, we also have to be cognizant of the nuclear security dimensions to this, because there is a non-proliferation security dimension to this. And so that kind of forms the kernel of my research. I like to think that I'm interested in some of the big problems in terms of the social impacts of nuclear energy. But my interests lie at the intersection really of fuel cycles and waste management, as well as applying advanced reactor physics methods to the problems of the fuel cycle, and bringing into bear an understanding of nuclear non-proliferation safeguards, such that we can make sure we can apply these techniques and be assured that malefactors aren't using this, for example, or misusing this to produce weapons material. So what lies in the intersection are some of the things I do, such as fuel cycle modeling and waste management and safeguards for advanced fuel cycle facility, which includes things like measurements we conduct on spent fuel and material accountancy for spent fuel and reprocessing facilities, as well as some novel applications for applying reactor physics methods. So let's get to the meat of the talk now. Where are we and how did we get here? So my goal here is really to present first an overview of what the nuclear fuel cycle is and how we got to the present day from where we started. So the nuclear fuel cycle really, the nuclear fuel cycle, or the cartoon version that we have in the United States, starts off at the uranium mine. So we see here, basically we extract uranium ore from the ground, we mine it and process it and mill it, and then, though, to use uranium in reactors, we need to separate out the more usable uranium isotopes. So uranium, most uranium in nature comes in two flavors, the lighter U-235 isotope and the heavier U-238 isotope. It's U-235 that's usable in reactors, at least the kinds of reactors we use today. So, with the exception of Canada, that runs a different kind of reactor, most reactors in the world have to rely on enrichment of uranium to maintain criticality. So once we've enriched that uranium, we can then fabricate that into fuel for reactors and irradiate it. And so the idea goes, then we would, once it's sufficiently cooled down, we would package it up and dispose of it deep underground in a geologic repository in order to sequester it from the environment and from humans. Now, this is not where the story ends, though. That's the physics that we have, that we've known about since the 60s, has always envisioned a more complete version of this nuclear fuel cycle, where we take full advantage of the energy content, not just of the lighter U-235 isotope, but of 238 as well. So the idea of this, of course, would be instead of just simply throwing it away, that we take that used fuel and chemically separate it out to get out the heavier we call the actinides, the bottom of the periodic table that are left in the fuel, the long-lived component of the waste. Then we separate that out, make new fuel, and recycle it in fast reactors or advanced reactors that can take advantage of that actinide content in the spent fuel. And continue doing that and only throw away the parts of the fission products, the residual wastes, that we can't use as fuel, which is a much smaller waste stream, and as I'll show, much shorter lived. However, right now we're not there yet. In fact, the only countries to even approximate this model are France. And France actually doesn't use this advanced reactor type. They actually recycle fuel and send it back to their conventional reactors, which means they can only go one or two passes before they end up throwing it away entirely. So they too do not have really the fully closed cycle that we've been aspiring towards. But here in the US, we don't even have the one-through cycle. We have this. We have spent fuel that's kind of stuck in the reactor with nowhere to go. How did we get there? And how do we get to here? That's where I'm going to go first. Because ultimately, where we want to go, though, given the difficulty of doing this, ultimately we want to eliminate as much as possible the need for repository by transitioning toward a more fully closed cycle. So before we get there, I want to talk a little bit about how we manage spent fuel in the interim. So right now, we have been managing spent fuel in pools and casks after it's irradiated in the reactor for many, many years. So we've been doing this since the 60s. And we have a good understanding of how to manage spent fuel. So after fuel has been irradiated in the reactor, we can store it in very deep open pools like this. These are pools filled with water. And by simply circulating the water as the spent fuel latent radioactivity cools down, this fuel can be stored safely on site. So basically, the water is serving two purposes here. First, it's serving to actually cool the fuel, because even though we turn the reactor off, there is still a good amount of decay reactions going on. So for example, the minute you shut the reactor down, the fuel is still about 7% power, just from all the short-lived decays going on in it. So generally speaking, fuel has to be cooled for about 5 to 10 years in one of these pools before we can do anything else with it. After that point, it's fairly cool, thermally cool. It's still radioactive enough where it's a problem, but on the other hand, thermally, it's cool enough where we don't really have to worry about it melting or otherwise deforming, or in essence, being potentially hazardous in terms of, say, a catastrophic accident somewhere. So once the fuel is cooled for about 5 to 10 years, we can move it into stainless steel and concrete canisters and casks. So this is an example of a dry cask yard here at a spent fuel dry cask yard. So the idea is we take a crane and load these kind of canisters underwater, which provides a shielding, load these very thick stainless steel canisters, which are then wrapped in a concrete overpack, which provides both physical protection from the elements as well as providing radiation shielding. And so just kind of for scale, there's a person there for scale here. So these casks then, we have studied these quite considerably, and we found that, so the way these work then is they're then cooled by natural forces. So if you look very closely, you can see little vents in those casks. What those do is those allow air currents to flow in and circulate air out through natural convection. So natural forces will carry away the heat being generated by inside that canister. But the idea here is those stainless steel canisters are completely welded shut. So the spent fuel is in there, it's welded shut, and we found that once the fuel is this cool, we found that based on studies that were conducted at the national laboratories, that this can be stored on site safely for the periods of decades. But this is not a permanent solution. The fact is that a concrete cask sitting on a pad will work for the interim, but it's not a final solution. The fact is we cannot guarantee isolation from humans and the environment for the hundreds of thousands of years required for the spent fuel reactivity to go down to natural background levels. So this is really only a temporary solution. It's temporary on the order of decades, but what we need are more final solutions. So just as a quick aside, so we often talk about spent fuel pools, but what would happen if you actually dived into a spent fuel pool? I love this explainer cartoon by Randall Munro, and the answer is, assuming you're staying within, say, outside of the 10-foot range, you're probably going to get less dose inside that pool than outside it, because water is actually a very effective radiation shield. It's dense, and very dense materials are great at stopping gamma rays. It's really, you're going to get, it's only when you start getting close to the fuel assemblies that you start having a problem. So this water, in addition to providing the cooling, is really also providing your radiation shielding component as well. So before we continue, we really need to talk about what is spent fuel. To understand what spent fuel is, it's first useful to start out, what do we start with here? So what typically goes into a reactor might be about 96% still of that uranium-238 isotope, that heavier isotope we don't use for the fuel, and about 4% U-235, that lighter isotope that we enrich up. So in natural uranium that we pull out of the ground, the U-235 isotope is less than 1%. It's about 0.7% in nature. So we enrich up about 4% to use in a reactor. After it's burned up in the reactor, our spent fuel looks a lot like this. About 93.5% of that is still uranium, where we depleted out the U-235 isotope, but it's still mostly uranium. The other 6.5% is the stuff that is created through the reactions. About 5.2% of that is fission products. Another 1.2% of it is plutonium, and then 0.13% of the minor actinides. So the uranium itself, not very radioactive. Assuming you don't eat it, it's not going to be a problem. Uranium is mostly the bulk term here. The fission products are very radioactive. These are the problem nuclides. These are the reasons that, designed to get the full idea to go up on top of spent fuel assembly, it will kill you in minutes. It's because of these guys. That said, these also tend to decay away much faster. So by about 500 years, they're mostly gone, which leaves the plutonium minor actinides. These are somewhat radioactive, but they're very long-lived. these are where we're concerned about the geologic disposal problem. So when we talk about spent fuel being radioactive for hundreds of thousands of years, what we're really talking about is this 1.5% of the spent fuel right here. And these guys are not necessarily radioactive in the same way. They don't give off a strong dose that if you stand next to them, that they're going to hurt you. The kind of radiation they give off tends to be heavier particles like ionized helium nuclei, which we call alpha particles. The real danger here is ingestion, that if they get into groundwater or food, then we ingest them, that they'll cause potentially problems like cancers. And so we need to be able to isolate these from the rest of the environment. That said, these may also be usable as new reactor fuels. So these are both what drive our long-term disposal challenge, but also would present an opportunity to look at other ways to treat nuclear waste. So managing spent fuel is a daunting challenge, but it's a daunting political challenge. What you see here is kind of a net kind of projected set of spent fuel discharges from the current U.S. fleet here on the left. This is, of course, out of date. This is last updated in 2001. We're actually much closer to the 70,000 metric tons mark here. So 70,000 metric tons is, 1 metric ton is 1,000 kilograms. This looks like a lot. 70,000 metric tons sounds like an awful lot. Actually, though, in terms of volume, it's not that much. If you stacked it end to end, about 3 meters high, you're not even going to fill a football field. It's not a very big volume of waste. That said, it's still a challenge to be managed. But meanwhile, one issue here is that we've been filling up these spent fuel pools as talked about. Almost all reactors now have filled up the original allocated capacity at the spent fuel pools because it was always assumed when we built these reactors that we were going to take away the fuel away and potentially reprocess it. We haven't done that. In fact, we haven't even taken it away and disposed of it yet. So a lot of these reactor operators now are being forced into the position of taking their fuel and putting it in dry casks because they're simply out of space. And they've actually, as a result of that, they have been suing the federal government and winning because the federal government made a promise to them in 1984 that they were going to start taking that fuel in 1998. And that didn't happen. And we're going to talk about that. So just looking at the time scales that we need to manage spent fuel on, this is just the activity in terms of the amount of radioactivity per unit mass of spent fuel. And so you can see here what's happening is the first about 500 years, almost all the activity is being driven by these fission products. In terms of the amount of reactivity being given off in the spent fuel, it's almost all fission products. But by the time you get to about 1,000 years, it's already being dominated by the actinides, the uranium and plutonium, and all these things at the bottom of the periodic table. We start seeing a shift there. And from then on, almost all of your activity is being driven by that out to the 1 million year mark. And if we look at the actual toxicity index, in other words, how much hazard is this if it's ingested? What's driving your hazard actually is going to be a very small set of elements. So in the first, say, up to about the first 1,000 years, what's going to dominate you are going to be isotopes like cesium. So cesium is one of your major gamma contributors. It's going to give a strong external dose, but it has a half-life of about 30 years. So after about 100 or so years, most of the cesium begins to decay away. So by 100 years, you've gone through 3 half-lives. So that means we've gone through 1/2 times 1/2 times 1/2, or 1/8 of the original activity by 100 years. So by 300 years, it's effectively gone. Meanwhile, though, we begin to see kind of the creeping in of isotopes like americium that decay away from plutonium, and of course we see plutonium and curium, and these will drive your hazard from spent fuel out to that 1 million year mark. So these are really the problem nuclides. And I've put here for comparison here this dashed line uranium ore. So this is the comparable hazard from the unmined ore. So in other words here, if we did nothing and left the spent fuel, left the uranium fuel in the ground, that would be the comparable hazard to this. And we see here that it crosses at somewhere around the 300,000 year mark, where the hazard is no greater than if we never pulled it out of the ground. So we're kind of using that, in essence, here as our baseline standard for when does the risk from the exposure become acceptable. So the Nuclear Waste Policy Act, as it was passed in 1984 and it was amended in 1987, specified Yucca Mountain in Nye County, Nevada, as the nation's sole repository for spent nuclear fuel. So in other words, we made an executive decision that we were going to abandon the idea of processing and dispose of fuel in the ground at Yucca Mountain. This was a controversial decision when it was made, because it was made over the objections of the Nevadans. Nobody asked them. In fact, we asked them, they said no, and we said, well, we're doing it anyways. So this was a controversial matter. In 2009, the Obama administration announced plans to formally abandon Yucca Mountain. That this was, during the Bush administration, the final license was was submitted to the NRC. The Obama administration attempted to withdraw the license application, and eventually the court said, no, you can't do that, but they effectively zero-funded it. So as it is right now, while Yucca Mountain still is on the books as our official strategy for managing spent fuel, it is effectively dead in the water for right now. So, as a result then, in the next year, President Obama convened a Blue Ribbon Commission to chart a new course for spent fuel policy. I say that sort of. And the idea is that we're still generally on track to look at disposal as an official policy option here. So this consisted of pulling together experts and stakeholders from a variety of communities, including experts in nuclear engineering and the nuclear fuel cycle, experts in non-proliferation, representatives of the utilities and labor unions and the like. Had three main subcommittees, including the Reactor and Fuel Cycle Technology Committee, Transportation, Storage, and Disposal. So the Blue Ribbon Commission looked at the options for spent fuel management, and one of the big things they stressed was the need for a more consent-based siting process. They pointed specifically to examples in other locations such as Sweden and Finland, where it's a more community-oriented process, and these countries have actually had some matter of success in siting a geologic disposal site. So these will probably be the first countries that successfully operate geologic disposal sites for spent nuclear fuel. It can be done. Other things they stressed were the need for site-neutral performance requirements, instead of, in essence, taking the example of the Texas sharpshooter fallacy, where shoots the gun at the side of the barn and then walks up to it and draws the target around where his shot landed. This was the perception of Yucca Mountain, is that, okay, we picked a site, now let's tailor the performance requirements around the site we picked. What the VRCs kind of indicated was, no, you really need to lay out your criteria first, then pick your site and see, does it meet the performance criteria? And likewise, they stressed the need for a more flexible process, so that things do go wrong, that we can back up, stop, and reconsider our options instead of charging forward. So they recommended a number of strategies, including looking at a more decoupled waste management organization. So a federally chartered corporation similar to TVA that would control access to the nuclear waste fund, independent of Congress. So few people know this, but actually the nuclear industry does pay for the cost of waste disposal. So up until about 2 years ago, there was a tax levy on every kilowatt of nuclear electricity generated. So it was 1/10 of 1 cent per kilowatt of nuclear electricity. So this was paid into a fund managed by Congress called the Nuclear Waste Fund. With interest, it's accumulated about $30 billion in balance. They've spent about $13 billion in the process of characterizing Yucca Mountain. Finally, the utilities challenged it after the Obama administration decided to pull Yucca Mountain, arguing, well, look, if we're not going to get a repository, we shouldn't have to pay this tax. And district court agreed, and so the Secretary Moniz set the waste fee at zero about 2 years ago, and it's been there since. But the idea of the BRC was saying, okay, instead of making the waste management organization go to Congress for approval every year for their budgets, give the money to some federally chartered corporation that could manage the budget independent of Congress. And meanwhile, establish, in the interim, while we get our act together, for deciding repositories some kind of centralized federal site to start taking possession of spent fuel from the utilities as a short-term strategy so we begin meeting our obligations under the Nuclear Waste Policy Act. One thing they declined to do was endorse any technical alternatives. They didn't comment on the viability of the mountain. They didn't comment on technical strategies for managing spent fuel or recommend processing. This was too contentious within the committee. There were too many divided opinions on the merits of different technical approaches. So in the spirit of that today, I'm going to present to you kind of both prongs of the approaches we can take without necessarily advocating for one or the other, although I definitely do have my opinions. So in 2013, the DOE responded to the Blue Commission and said, yes, let's do that. So now this is kind of the policy we have moving forward. So the schedule they proposed is by 2021, begin starting up pilot operations of a centralized interim storage site. By 2025, begin operation and start taking spent fuel assemblies from reactors all around the country. By 2048, have a target date for a repository. Only 50 years after the original scheduled date. Meanwhile, they emphasized many of the findings of the VRC, including the new need for a more decoupled waste management organization and a more flexible and consent-driven siting process. That is, going to communities and asking them to volunteer and not saying, we're volunteering you, because rarely does that work out well in practice. So meanwhile, in the interim, until we get that repository going, or until we figure out another strategy, we're going to be relying a lot on dry storage modules, like I just showed you here. And the idea here is that, again, we're relying on the fact that the spent fuel has decayed long enough to be cooled for the natural forces. It's still radioactive enough where it needs the shieldings, these big concrete shields, which also provide protection from natural events like floods and tornadoes and other kinds of potential hazards. Current ongoing studies at places like Idaho National Laboratory and Oak Ridge National Laboratory have indicated that we can safely store spent fuel this way for several decades. But some of the issues we still want to make sure we can work out are things like the material degradation mechanisms. So, for example, as we're going to have temperature cycling in these casks through the seasons and through the days. And so some things we want to make sure of here is that we're not seeing adverse material evolution, such as the cladding becoming brittle due to this temperature cycling and due to this radiation damage. And so these are where the main focuses are now, as far as the science of spent fuel storage, is making sure that we're not seeing unpredictable or unanticipated changes in how the spent fuel behaves in terms of materials on the pad. Because the last thing we want to do is transport this from, say, one site to another, open up the cask and repackage it to find spent fuel crumbs. You do not want spent fuel crumbs. So, a bit of an interlude here. Everyone has an idea to deal with spent fuel, and most of them are terrible. So, how not to do things? How not to do things. So, the government is nagging us to get rid of our spent, dangerous, radioactive waste. On a totally different topic, I'm giving you each a motivational paperweight that says, nice going. Try to avoid licking it. Probably the best advice I can give you as far as spent fuel management, try to avoid licking it. So one common option that comes up is, well, why can't we just throw it in the sun? Why can't we just blast it into space? The reason, we're not that good at rockets yet. So not only is it very expensive per unit payloads, we're talking about uranium is one of the more dense materials. It's got a lot of atoms in a small space, which means it's very expensive to get it in space. Even assuming you do that, I'm not sure I trust launch vehicles enough to try relying on that strategy. So it's, generally speaking, not a desirable strategy. I hear this one a lot too. So why can't you just throw it in a volcano? Well, just throw it in a volcano, you're done, right? But the problem is, volcano isn't actually doing anything to change the radiological properties of spent fuel. Right? This is probably the worst idea you could think of, because it's probably one of the most effective ways to make sure you scatter that radiation everywhere you can go. Everywhere it can go. I would you know, the whole problem is it's not actually going to isolate spent fuel and radionuclides. It's going to do the opposite.
Anybody actually proposed it?
I'm not saying scientists proposed it. I'm saying laypersons proposed it. Ice sheet disposal, I might be being a little unfair by lumping this in. So this is a more serious idea that was actually investigated by the national academies when they were looking at options for spent fuel disposal. It's a clever idea. Spent fuel makes heat. Well, heat melts ice. So if we can simply use the heat of the spent fuel to melt through the glacier and put it at the bottom of the glacier, it'll stay there stuck down at the bottom of the glacier where nobody's going to try and dig at it, and it's going to be nice and protected from the environment. The problem is that glaciers are melting. Glaciers move and glaciers melt. That's the problem. So this is, and it's also, of course, this is not a very politically palatable solution. So let's move on now to the heart of it, is kind of where are some of our most technically robust options for managing the use of nuclear fuel? And those strategies really come down to two basic ideas. Is spent fuel waste, or is it a resource? And how you make that consideration determines what way you want to go, what trade-offs you're willing to accept for that. So that comes down to two roads. We can either go the direct geological disposal route and dispose of spent fuel in its intact form deep underground, so in mined cavities or deep boreholes. The idea of this is just to simply put spent fuel down below where it can get out into the environments and where it's contained for long enough that the reactivity decays away. Or we can partition out the useful species and try to transmute them in advanced reactors. So the idea is we separate out that long-lived component, burn it as fuel, and dispose of the stuff that's radioactive over a shorter time period. Now, to be honest, I'm giving short shrift to the variety of options we could use to iterate on this in general, simply because I'm limited in terms of time. So geologic disposal it really relies on the idea of trying to sequester this material as long as possible. And our strategy comes down to running up the clock. So our idea is to get this spent fuel contained, everything that's spent fuel held on to long enough to simply run up the clock on the reactivity. So this means throwing out every delay we can. It's really like, it's very similar to the sports analogy here. It means, in essence here, running off the field to let the clock going here. Okay, I'm really bad at sports analogies now. But the idea here is we're trying to just hold the spent fuel in one place long enough that it decays away and is no longer presents a problem. So we do this through two kinds of systems. We do this through human-made systems or engineered barrier systems, like the waste package itself and the overpack that acts as a shield to prevent water from getting in. The backfill, like for example, clays and other things that we use to absorb water and absorb the radionuclides if they get out. And other things, like for example, the Yucca Mountain concept rely on a drip shield to deflect water away from the waste package, again, to prevent the corrosion and leaching that would occur in that waste package. We also rely on nature itself, and in fact, in very long time periods, that's what we're relying on is the forces of nature. We're relying on things like the natural geology features, so for example, the chemistry of the rock we're dealing with, and the hydrology. The hydrology is really what determines how a geologic repository works. And so this is the basic idea here. In the water cycle, the water we typically interact with is between the water table and the first confining layer. This is water that has cycles on the order of days to years. If we go down below the confining layer into confined aquifers, now we're talking about primordial groundwater. Groundwater might have been there for centuries because it takes a very long time for water to permeate these layers of packed clay, etc., and bubble the way back up. And if we go even deeper, we can find really, truly ancient water. Water that's been deeply confined. And so we can take advantage of this, as well as the fact that we know a lot about the chemistry. So we know a lot about the dynamics of water in these kinds of systems. The challenge here is understanding and being able to characterize how this water will flow in the system we're talking about. But if we can get a handle on the flow rate of the water and the chemistry of how things behave in here, we can take advantage of this, for example, to slow the motion of how fast water can get into our package and how fast or how slowly things will leach out. So for example, if under the right chemical conditions, we will have our solubility, how much of the radionuclides we can dissolve will change. So the right conditions will make it less soluble in water. The wrong conditions will make it more soluble. The right conditions will mean that our geology is sticky. It wants to hold on to those radionuclides, which again slows their progress down. The wrong geology will let them pass right through. And that's why we need to be very, very careful about the geology and the hydrology when we talk about these kinds of sites. So the Yucca Mountain disposal concept really relied on these kind of engineered barrier systems along with the natural geology. So it was these drifts underneath the mountain with the spent fuel in canisters surrounded by the waste package. And then of course we have the titanium drip shield to deflect water from there to get to buy us more time to prevent the corrosion. And it was backfilled with materials like clay to help absorb water and radionuclides as they leached out. So the Yucca Mountain disposal concept really relied on some very sophisticated material alloys. So we used an alloy called alloy 22, which is a nickel-based alloy that shows incredible corrosion resistance. This is a picture of an alloy 22 coupon that's about 50 years old. It was exposed to a marine environment. With minor polishing, it shows a mirror shine. So this is a very advanced corrosion-resistant alloy, and it was really used as our strategy in the U.S. with Yucca Mountain, is trying to prevent this package from failing for as long as possible. Other countries, like Finland and Sweden, have relied on other materials like copper. So we know, for example, based on studies of copper in nature, that copper shows very good corrosion resistance properties. And so Sweden and Finland have relied, for example, on a waste package made of copper. And with the idea here of delaying the ingress of water for up to 10,000 years or more, but making this copper thick enough. And the spent fuel would go into that lower package. Their disposal concept then relies on disposing it in granite bedrock, which has very good mechanical strength and very good chemical properties. And this would be down, the drift structure would be down about, on the order of about 200 to 300 meters below the ground. So we're talking of deep, deep underground. So again, to stress, these are successful projects. These are projects that have been supported by the community because they came and asked the community first and were very open about the process of what they wanted to do. Another alternative is deep borehole disposal. So this relies on the fact that with the advent of hydraulic fracturing and oil and gas drilling, we've gotten very good at drilling very deep holes. So deep borehole disposal looks to go 10 times deeper than any place like Yucca Mountain. So we're going way, way below the water table down to crystalline bedrock to dispose of waste packages. So the idea here is that because water would take so long to get down here and back up, again, we're running out the clock before anything dangerous can get back to the surface. So the scientific challenges we have for this include understanding how packages corrode and degrade over these kinds of extreme time horizons, understanding the hydrology and geochemistry in the drift and beyond, and being able to appropriately assess how these packages will fail, because they will inevitably fail. How does that affect the performance of the repository as a whole? So eventually the water will get in. There's no stopping it. The question is though, what happens then? What happens when the water intrudes and begins to seep out? How does the repository then work to slow the migration of these materials until we buy ourselves enough time for the material to decay away? So partitioning and transmutation takes a different strategy in this. If you can't run down the clock enough, then start shortening the timer to begin with. So the species we're interested in, most of the hazard is from these four nuclides right here: neptunium, plutonium, americium, and curium. Most of your hazard over the long time horizon occurs right here. So for example, in the Yucca Mountain Science Engineering reports, the first 25,000 years, yeah, you have two problem nuclides, iodine and technetium. These are fission products. They are very mobile in water. So these are contributing most of the dose when the package fails. So right around what we see here, for most cases, it's assumed the package will fail somewhere after 10,000 years. As you get to longer time horizons, though, where this big curveless dose begins to occur from now, are things like neptunium and plutonium. And by about 100,000 years, the dose here is almost exclusively driven by neptunium and plutonium. Neptunium in particular is very slippery. It likes to just slide right through groundwater. It's very hard to stop. So that's what would be driving the dose there, is those nuclides down here at the very long time horizons. Now the stress, these are actually, this sounds scary, but we're actually talking about relatively low doses here compared to the natural background we get from cosmic sources and from the sources on the Earth. For example, the natural reactivity that occurs in the ground. But the fact is, though, is that we can still get this number down. We can still have a higher assurance if we can take these components out of spent fuel and use them for something like new reactors. So if we were to fission them, the lifetime we're going to manage this waste and be assured that everything is working correct can be dramatically reduced. We can shorten that clock. So we can do that via methods like the Purex process. And we've been doing this for decades. We have known how to do this kind of chemistry for a very long time. So again, this is a very cartoon version of it, so I'm sure there are details I'm omitting. But the idea is we chop up spent fuel pellets into an aqueous solution like nitric acid. It dissolves it into the constituent elements like plutonium, americium, etc. We then add an extractant like tri-N-butyl phosphate, which makes these into organic compounds. And the way to think about this is really as oil and water. Oil and water do not mix. And so if we can make these go from an aqueous phase to an organic phase, we can separate them out by separating out their oil and water phases. We can then skim those out and turn the rest of these very reactive components into glass to immobilize them. France does this today. The issue, though, is that France uses that to separate plutonium in their current fleet of reactors. And the problem is that it doesn't necessarily work too well. So this is just a little bit of a glimpse of the physics here. So what this really is the probability of a neutron fission versus a capture reaction. For plutonium-240, we have this giant peak right around where the neutron's energy is in our kind of current reactors. I call this the why we can't have nice things peak. This peak is what drives our long-term hazard. It's our bridge to all those problems, of those minor actinides that cause all the problems. So we start with U-238s. We add a neutron, becomes U-239. That will quickly decay right up to plutonium. Plutonium can either fission or capture a neutron, become plutonium-240, which will then capture a neutron, that giant peak, comes plutonium-241, which can then capture and go on and on, and make all those long-lived species we don't like. That's what drives our long-term disposal challenge right there. This is why it's hard to use our current reactors to burn the long-lived species, though, is because these reactions are all more favorable in the kinds of reactors that we run today. So DOE was aware of this and came up with a fuel cycle evaluation and screening study that said, okay, well, can we look at future options for nuclear R&D to prioritize this? And they looked at this and screened down all the different kinds of fuel cycles they could think of, included about 4,000 groups, and condensed it to about 40 based on different physics properties of the system. And came up and looked at, say, okay, which systems deliver the most benefits for the least amount of challenge? Starting from, say, our current once-through cycle to cycles like those practiced in France and beyond. And what they came up with here is the most promising fuel cycles, those that deliver the most benefit for the least amount of challenge from today, are those that looked at continuous recycle of uranium and plutonium in advanced reactors. So what would that transition look like? So the answer is it would take a while, and mostly because if we assume we don't separate out any fuel that's been discharged before 2010, we actually run out of material. We actually don't have enough plutonium to do this without starting up new light water reactors, because we assume the current fleet of light water reactors begins to retire at the end of their lives. We actually need new light water reactors to make enough plutonium to sustain this transition. We're kind of almost in a weird catch-22. We have to make more plutonium to start these reactors up to begin burning all the plutonium. Because these reactors burn out this material very slowly. They don't require much material in terms of recharge here. But the total transition time would take about 150 years. But that said, if we made a transition, we would have enough nuclear fuel to last us hundreds, possibly thousands of years. We would not run out of nuclear fuel until we discover some other energy source or leave the planet. So we've cut down the lifetime, but the important caveat here is this does not eliminate the need for some kind of disposal strategy for fission products. That said, by shortening the lifetime, we open up the possibility to rely more on human-made materials that we have more experience with, and less on nature. So there's less inherent uncertainty when we deal with shorter lifetimes. And meanwhile, the outlook for advanced reactors, there's considerable interest in these kinds of reactors, both from DOE and private entities, including Bill Gates' sponsored startup Terra. The terrestrial energy is looking at molten salt reactor variants, and some MIT students did their own startup called Transatomic with their waste annihilating molten salt reactors. There's a number of ideas out here on how we can get from today to the future. So I know I've already run over my allotted time tonight, so I want to just quickly wrap this up. So the outlook right now is that DOE and NRC are really looking at the ways that we can ensure safe storage of spent fuel in the interim. And right now, the science says that we can safely store this material for decades. But that's not a really satisfying answer, because it's not a permanent solution. Presently, the DOE is looking at centralized storage as a way to at least get it out of the reactor sites and centrally managed. And then looking forward then, how we can go from a system of once-through use and disposal towards a more sustainable cycle. So the big takeaway I want you to walk away with here is that this is not an unsolvable technical problem. We have an abundance of technically robust ways to manage that fuel. And then we're going to continue learning more. By studying more things like material degradation mechanisms, we can be more assured about the continued safe storage of this material until we solve the political problem of what do we do with it. Either developing politically acceptable strategies for geologic disposal, or committing toward the resources and political will towards a strategy based on recycling of the longer-lived wastes in advanced reactors. It's not going to totally eliminate the problem of nuclear waste, but by dramatically shortening the time frame, we can make this problem into one which is more manageable over time scales, more approachable by human engineering and human knowledge. So I'll leave it at that, and I'm happy to take any questions.
The we you're using is we here in the United States.
Right.
The bigger problem is there are now 7 or 8 nuclear powers with weapons, and everybody has a reactor or two around. The international problem is for controlling these things and controlling the technology for burial and partitioning and all that doesn't exist. I mean, we don't have a framework for that.
Well, yes and no. I mean, I would say we don't have, we do have a robust set of international safeguards. We have robust mechanisms, for example, for safeguards to monitor and measure the inventories of submarine materials in facilities. So, for example, Japan actually, until recently, has been pursuing a broad policy of separating out spent fuel and looking towards closer fuel. And Volcano, the separation facility, has been kind of a test bed for how we can demonstrate these kinds of technologies. But the issue, I think, the larger issue is, I think, as politically, is that a solution we want? Do we want everybody enriching fuel? Do we want everybody reprocessing fuel? That's a political question. I think there are technical strategies if we go that route. So, for example, South Korea really wants to pursue reprocessing right now. They're pursuing a technique I didn't talk about just due to time. but it's a separate strategy, but it's another partitioning strategy. They really want to do that because they're saying, look, we don't have a lot of space to dispose of spent fuel, and we're a little bit nervous about that because we are concerned with proliferation convention. That's where I think technical measures, though, I think either we need to come up with smart policy measures, like, for example, saying, okay, well, if we don't want you reprocessing the fuel, then we're going to take it back and we're going to reprocess it, and we will cut down the waste volume. Or we need to be investing in measures where we can make strong assurances that materials not being diverted out of that fuel cycle. And I think we have mechanisms, and I think we're continuing to improve those. That's an area I work on that I could give you a whole other hour talk on, but I think it's a salient point. I mean, the fact is, that is a dimension to this, and I think we can't ignore it, that all this is easy in the United States. It's because the fact is, we're a weapon state, we're not worried about the US government diverting some bombs. We are concerned about countries like Japan and South Korea, and then eventually newcomer states like Saudi Arabia. We are concerned about that. And I think in some cases we have legitimate reason to be concerned about that. And I think then it's a question then of how do we apply the technological and political solutions to that? Because I think I think we can't prevent proliferation through technical measures alone, but we can detect it occurring. And I think it's a really important fact, because if most countries are not, outside of North Korea, aren't going to openly admit to pursuing proliferation. Most countries they're not. Well, Iran even is trying to be subtle about it, right? They're trying to say we're not really doing that.
We have put them in the business too.
Right. Even like countries that we strongly suspect are trying to proliferate, or at least trying to make a plausible cover story they're not. And that's where I think really strong strategies to detect if materials are being diverted or misused. Then we can say we can nail them to the wall. We can verify, no, you're not doing what you're saying you're doing. That's where I think. And again, it's a whole other talk. The science of non-proliferation. I could give a whole hour talk on that.
Can I have one more comment? You have a great talk to advertise to the Baker Center. Why don't you do that? I mean, that's a totally different audience.
Well,
I think it'd be very instructive for the people who go to those things.
That's a whole other kettle of fish.
Let's all thank Dr. Skutnik. And hopefully I'll be back to talk on that subject.
Okay.